IPARCOS Institute colloquia. I would like to thank José Victor López Moreno for the technical support and Jesús Gallego for organization with the IPARCOS. And before the talk, I was just also to thank Professor Herdenayens, and I will briefly introduce her. She's a full professor at the Leuven University at the Institute for Radiation and Nuclear Physics. She's a world expert on measurements of nuclear moments and the use of atomic techniques for nuclear measurements with impact in nuclear structure. She's very well known in the community for her push to start measurements in world-leading facilities. This includes a former Louvain-la-Nef accelerator, but also GANIL, GSI, where she took part and had a leading role in G-factor measurements, and at ISOLDE also. And she's the physics group leader and ISOLDE spokesperson since 2017 of the ISOLDE facility at CERN. And her talk today will deal on the ISOLDE physics. So I leave the floor to her. Thank you for giving us this colloquia, and I will try to gather all the questions and comments on the YouTube channel and forward them to her. So if you could please share your screen and start, we go ahead with that.
Thank you, Luis.
Thank you.
Can you see my screen?
Everything is fine, thank you. Yes.
Okay, so then I can start. So thanks for the nice introduction. So it's a pleasure for me to give you a flavor of the physics we are doing at ISOLDE at CERN, where we are producing radioisotopes for a variety of research questions. So ISOLDE is taking protons from one of the accelerators in the big accelerator complex at CERN, so which are produced very soon, well now already, through a new linear accelerator where they are pre-accelerated before being injected in a booster, where they are now reaching energies between 1.4 and 2 GeV. And from there on, they are going to the bigger accelerators, finally reaching the LHC. So ISOLDE takes about 50% of the protons from the booster. The other 50% are going into the proton synchrotron and are from there accelerated further. So ISOLDE is CERN's radioactive ion beam facility. And we are producing the radioisotopes through the method of isotope separation online. And that's also giving the explanation for the name of our facility. The isotopes that are produced and that we can extract will have lifetimes of at least a few milliseconds. So if you want to read more about ISOLDE, we published very recently, last year, in the CERN Courier, a paper about the very first pioneering experiments at ISOLDE, because ISOLDE is CERN's longest living experiment. So it was initiated in the 60s. And one of the pioneering measurements that were done in the first 5 to 10 years were mass measurements and measurements of nuclear moments and nuclear radii using laser techniques. And these two techniques are still world-leading at ISOLDE because they have been upgraded continuously and are still being improved every day. So the playground of our research is the nuclear chart. So let me just introduce it. It's the isotopes are labeled with their numbers of neutrons on the x-axis and their numbers of protons on the y-axis. And the black dots here in the graph are the about 300 stable isotopes that we know here on Earth. Next to that, there's the yellow isotopes, and these are isotopes that have been produced most of them at radioactive ion beam facilities, and where they can also study their detailed properties. And however, there are about 3,000 more that are being predicted by nuclear models to exist. And these isotopes we have not been able to produce yet. And so one of the challenges in nuclear physics is with the new accelerators that are being constructed worldwide, like in Japan and in the US, is to really try to access as exotic as possible these neutron-rich regions, because these are isotopes that play, for example, a key role in the production of the elements in the stars. And so at the moment, we rely fully on nuclear models to predict their properties, which have a huge impact on these production rates, for example. So the quest in nuclear physics is to try to explain the existence and the organization of nuclear matter in general, and in particular to look at how the strong, the weak, and the electromagnetic interactions are working together to form bound nuclei or isotopes in the nuclear medium. We also use our isotopes to look if there's physics beyond the standard model. And we can also, as I said already, help in answering some questions on the origin of the elements. Finally, at ISOLDE, there's also a very extensive program to use isotopes as probes for materials research, but also to be used for medical applications, for example, to look for new isotopes for cancer therapies. The isotopes at ISOLDE are produced through the ISOLDE technique, as I said, and we are quite unique in the world because the driver to make the nuclear reaction is the high-energy proton beam, 1.4 GeV. And we send this beam onto very thick targets of all kinds of elements. But if we use, for example, uranium in a uranium carbide target, then through the high energy, 3 different nuclear reactions are produced, and due to that, we can produce more or less the whole chart of the nuclei. So here in red, you see some of the isotopes that have already been produced at ISOLDE with the color codes giving their intensities, and the lowest intensities going to the edges. So by now, we've produced about 1,300 different exotic isotopes or isomers, so long-lived states. We can also sometimes separate them for more than 74 chemical elements, and with half-lives more than 10 milliseconds. A typical ISOLDE target unit, just to give you an impression, here is a bar, and this rod is filled with some material which acts as a target, and the protons are sent through this bar. So in fact, most of these protons are flying through, and since a few years now, we have placed a second target behind it, where we then also irradiate with the remaining protons in a parasitic mode, use then this new target for the production of dedicated medical isotopes in the Medicis facility at ISOLDE. So the radioisotopes that are produced in the material here, they are diffusing out of the target through a little tube into an ion source, because the atoms that are formed when they come out of the target, they are mostly neutral, but to accelerate them or to manipulate them, we want them as an ion. And for this, we use different ionization schemes. And the most used one since now already 1994, and the most selective one is the resonance ionization laser ion source technique. So in this, ion source, we shine lasers into the ion source with different colors, and by tuning the laser frequencies to specific frequencies to make resonant excitations of the electron around the atom, and then finally to rip off the last electron through an ionization process, which can be resonant or non-resonant, we can ionize all the isotopes of one particular element. And then by sending that beam through a mass separator after we've accelerated it to about 40 kilo-electron volt, we can also make a separation in the isobaric range of the chart. And like that, in the end, we get one particular isotope. So in principle, we are able to get quite pure beams. Of course, in the reality, we sometimes have isobaric contamination still persisting. And so that depends from element to element and isotope to isotope. So here you see an overview of the ISOLDE facility. So we have the protons that can be sent on 2 possible target stations, which means that we can run 24 hours a day, 7 days a week, during several months, because when one experiment is using beams produced at one target station, the other target station is being prepared for the next experiment. And typically targets are changed every 1 to 2 weeks. So then the ions that come out are going through a mass separator, either a high-resolution mass separator or a general-purpose mass separator, and then they can be sent into different beamlines. So here, these 2 are only connected here, but all the other beamlines are connected to the 2 separators and can accept different beams. So here in the low-energy side of the experimental hall, we have different beamlines, and each beamline hosts an experiment which is dedicated to specific types of measurements. We can also further accelerate the beam by charge breeding it and then producing post-accelerated radioactive beams. This has been done already since 2001 at ISOLDE, when the first accelerated beams were produced. This was with a small normal conducting linear accelerator that was constructed, and the energies that we could reach at that time was 3.1 MeV per nucleon. And this has been operational until 2012, when the first long shutdown of CERN started. During the long shutdown, preparations were made to also further extend the accelerator, and this has been started then after the shutdown in phases. So every winter we have added 1 more cryogenic module, which hosts superconducting cavities for further acceleration of the beam up to 10 MeV per nucleon. At this accelerator, we have now 3 experimental beamlines with dedicated setups for different types of experiments with reaction experiments with nuclear isotopes. As I said, we have a very diverse research program with the radioactive isotopes. So here we have the general pie, and about 14% of the experiments are on nuclear structure from beta decay, and about 20% are on nuclear structure by measuring ground state properties such as masses, radii, moments, and spins. Another 30% of the beam is used to be further accelerated with the high ISOLDE post-accelerator. And then different types of experiments can be performed. Mostly Coulomb excitation was done in the past when we had only the low energy radioactive beams. But since 2016, we can also do experiments with higher energy, and in particular transfer reactions are benefiting a lot from these higher energies. And there's also a scattering chamber where we can perform reaction experiments with user-specific detectors inside. Finally, the remaining time is given for applications, and these are to use the isotopes as probes for solid-state physics, so materials research, but also for medical physics or biophysics, or in the past, this was also for the production of radioisotopes, although that aspect has now been taken over by the Medicis facility. Let me start by showing you some experimental results from some different experiments, and I will start with the accelerated beam experiments, where people are making reactions with radioisotopes, and typically in a reaction you have a projectile, you have a target nucleus, they will interact with one another, and the reaction products will come out of this reaction. Depending on the energy, you will have a different impact parameter, and what you will typically measure in such experiments is the scattered projectile nuclei and target nuclei, but also the emitted particles from the isotopes that are being produced, which can be beta particles or alpha particles, and of course also gamma rays. So the goal is very often to measure precisely the cross-sections of the reactions, from which then nuclear structure information or other types of information on the nuclear reaction can be deduced. So with the low energies up to about 5 MeV per nucleon, the experiments that are being done are mostly Coulomb excitation experiments, and that is also what was done for a very long time until 2012 using the REX accelerator. It allows us to study, for example, vibrational and rotational behavior of nuclei, and also to study nuclear shapes. Also, already in that period, the people were doing scattering experiments in the scattering chamber, because this is possible with energies also between 3 to 7 MeV per nucleon typically, although higher energies can be used as well, but it's possible with the low energies also. And this is, for example, typical for astrophysics, but also to study halo nuclei, for example. And finally, transfer reaction experiments have been done mostly since ISOLDE became possible, because ideal energies for transfer reactions are with energies above 5 MeV, and so this was only possible since 2016. So I will first just show some results from REX ISOLDE, so from the first 10 years of operation, and there the detector that was used for all experiments was the MINIBALL detector. So as soon as the idea grew to build an accelerator, there was at the same time set up a collaboration to build a big ball of germanium detectors, and in particular segmented germanium detectors. So the array consists of 8 high purity triple clusters. So every detector is a cluster of 3, and every segment is again further 6-fold segmented. So it allows to have a correlation between the gamma ray that is emitted, and not only between its energy, but also with the direction in which the gamma ray is emitted. And that's important, for example, to make Doppler correction in the data. Inside the ball, they also have placed a silicon strip detectors, double-sided, which can then be used, for example, to detect the recoiling target and beam nuclei. Here you see a picture of the whole MINIBALL in operation. So here the beam is coming from this direction, goes through the vacuum tube, enters in the vacuum chamber where the particle and the target, particle detector and the target are hosted. And then here you have the germanium detectors from MINIBALL, as well as a high purity Clover detector at the end to look at the forward angles. So one of the physics cases that has been studied for several years and is still ongoing, in fact, is the study of to search for pear-shaped nuclei. Such pear-shaped nuclei have been predicted to exist in the nuclear chart in a few regions, and one of the regions here is in this heavy mass region around radium. So as you see, this is a fully yellow region, so only radioactive isotopes exist here, no stable ones. So such studies could not start until we had beams of radioactive of these elements available, such as REX ISOLDE. Also here in the neutron-rich region around tin 132, this here is tin 132. So here in this region, which is also in a neutron-rich region, but also a little bit closer to stability, there's a region where these things are predicted. So what is octupolar pear-shaped deformation? Well, you can have most of the nuclei have some deformation, but the more common deformation is what is called the quadrupole deformation. So an oblate shape like a pancake shape, or a prolate shape, which is more a rugby ball shape. But a deformation that is not symmetric, which has a pear-like shape, so here you don't have this up-down symmetry, this is called octupole deformation. And so this deformation is interesting in nuclei to look, for example, for physics beyond the standard model. So identifying which isotopes in the nuclear chart do have this kind of static octupole deformation is important, not only to understand the structure of the nuclei, but also for other applications in research. So First experiments that were reporting this kind of octupole shapes was coming from the ISOLDE experiment, where it was shown that the isotope of 224 radium indeed has the properties in its gamma ray spectrum that are reflecting a pear-like shape. So here you see this was the first time that this was experimentally demonstrated by looking at the different excitation gamma peaks in the spectra on different targets and then comparing the results with nuclear models. So at ISOLDE, which started more recently, in fact, in 2016, after the large shutdown of the first large shutdown, we have now higher energies available. So it means, first of all, that we can perform a much more efficient Coulomb excitation experiments, and I will show you an example of that. But also we have now access to different reactions like transfer. So just to show the impact of the higher energy, this here was the spectrum that was taken already in 2015 when one cryo module was installed after the long shutdown. And the very first beams were accelerated through the superconducting LINAC of this with this one cryo module. The gain in energy here was going from 2.8 with ISOLDE to 4 MeV per nucleon for the first after one cryo module. And the spectra you see here is the red one, is the spectra taken with the old accelerator up to 2.8 MeV per nucleon. And the blue spectrum is with the one additional cryo module with the higher energy with 3 times shorter measurement time. And what you can see are two things. First of all, the peak of interest here is the excitation towards this first excited state of the zinc radioactive beam. The intensity is the same with 3 times less measurement time. But more importantly is that the peak here, which is the second excited level, which was not at all visible with the low energy beam, was nicely visible here with the high energy beam. So by increasing the energy, you have access to more excitation energy, and that makes the analysis of these data a lot more comprehensive and complete. So the real physics experiments started then in 2016, after a second cryo module was added in the winter of 2015-16, and the first beams were accelerated on the 9th of September, and people were very happy about that. And this was followed by 5 experiments using 5 different radioactive beams that were accelerated, one even to quite high energies of 6.8 MeV per nucleon, and 2 experiments were used here, the scattering chamber that I mentioned, and the MINIBALL detector. So in 2018, the whole ISOLDE accelerator was finally completed. So we have now 4 cryo modules in place. And also we have now 3 beamlines fully operational with 1 new experimental station added in 2018 and also used for experiments just before the long shutdown. And I will show you some results from this as well. So on the second beamline, a large superconducting magnet, which you see here a picture of, has been installed. This superconducting magnet, in fact, is a former MRI magnet from a hospital in Australia, which was brought to ISOLDE in 2017, which was then fully stripped inside to be prepared to host a particle detector. And the advantage of putting a target and a particle detector inside a strong magnetic field is that now the particles that are emitted after the reaction, they don't go just straight into a detector that you put normally behind here, but now they are spiraling inside this strong magnetic field, and then they can be hitting a particle different silicon detectors, for example, on the axis when they reach this place. By doing the reconstruction of these tracks, you can get a much better resolution in the spectra. And so here, for example, you see a spectrum measured with a fixed target. So these are excitation levels produced in the reaction of, for example, 207 mercury beam. Well, this is not that example, but you could use, for example, a 207 mercury, 206 mercury beam, and then send it on a deuteron target. And then what comes out are protons and newly produced isotopes of 207 mercury. So the advantage is that the excited levels in these new isotopes are much better separated if you use this solenoid technique. So the first experiment, or one of the first that was done when this became operational, was indeed to accelerate a 206 mercury beam to the highest possible energy at that moment, 7.4 MeV per nucleon, and to send it on a deuterated polyethylene target, so a deuterium target. So the protons are scattered from the reaction, and 207 mercury isotopes are produced. Here you see where it's located. So it's in fact not very far from the value of stability. It's just a few nucleons away from the W magic 208. However, until this experiment, nothing was known on its excited states. So this was the first exploration of excited states in 207 mercury through this reaction. So here you see the reaction channel. And here you see a typical spectrum that was published, where also angular distribution measurements were done for these gamma transitions. And from this, spins and parities could be assigned. And so single particle levels could be identified in this isotope and then compared to nuclear theories. And with that, they could predict that for the n equals 127 isotones, so if you go deeper and deeper in to the more exotic nuclei in the chart here, the theory predicts that the last bound neutron, the last, let's say, isotone that has a bound neutron of 127 neutrons is the isotope of gadolinium. So the element gadolinium has 64 protons, and it's the last element to which you can bound 127 neutrons. And this was a result that is important, for example, for the astrophysics. Now, on the low energy side, I said we have many experiments. And here you see a flat ground of the facility, the low energy facility. So all these are low energy experiments where there are permanent setups located. And now I will just show you a few examples of some of these experiments. So we have a setup that is dedicated to mass measurements. It's existing there already since the 70s, initially, since the 80s. Initially it was a penning trap, but now it has been extended also with the multi-reflection time of flight mass spectrometer, and it uses different detection techniques that have been for optimizing the sensitivity of the measurements more and more, as well as the precision in some cases. We have a dedicated decay spectroscopy setup, which has been put together by a collaboration in 2015, and which is very modular, which has dedicated gamma detection, beta detection, alpha detection, neutron detection, and which is used depending on the type of a decay that the people want to observe. We have 3 experiments, well, in fact, we have 4 experiments, but 3 most very currently routinely used experiments for laser spectroscopy to measure nuclear moments, nuclear radii, and nuclear spins. There's also an experiment that aims to look for new physics beyond the standard model. This is the Wizard experiment. And there are many different smaller experiments to look inside materials, to look at the magnetic properties, the location of impurities in materials, using a variety of techniques. So just a few examples. Let's start with the mass of nuclei. So when we measure masses of nuclei, they give us access to how well nucleons are bound inside the nucleus. Because if you look at the mass of the nucleus, which is composed of Z protons and N neutrons, then the sum of the masses of the protons and the neutrons is in fact heavier than the mass of the nucleus. And the difference in energy is the binding energy. So this binding energy here is negative. And so by binding protons and neutrons in a nucleus together, the weight of the nucleus is lower than the sum of its constituents. So then by comparing masses of different isotopes, by adding, for example, more and more neutrons, you can look how much energy is needed to bind that last nucleon to the nucleus. As an example, I show you here the binding energy of the calcium isotopes, starting from the stable calcium 40 all the way up to calcium 56. So the stable calcium isotopes are those ones here, and so you see that the binding energy is gradually decreasing as you add more and more neutrons, and then as you are crossing, well, in fact, nothing much is seen here. You just see a gradual decrease of the mass. Note that these last measurements here are dating from very recently. So this is from 2013, and these here are measured in Japan in 2018, while these measurements here were done many years ago. So what is important is that in the chart of the nuclei, there are magic numbers. I think I forgot to stress that in my introductory graph, but magic numbers are appearing for protons and neutrons, a little bit similar, like you have more stable configurations of the elements, like the noble gases, for example. So there you have magic numbers of electrons. Here in nuclei, we have magic numbers of protons and neutrons. Now, 20 and 28 are known to be a magic neutron number in nuclei. And this is well shown in the mass measurements if you plot not the binding energy, but the difference in the binding energy between two isotopes with 2 neutrons difference in their core. And so this is called the 2 neutron separation energy. And then if you plot it, you see that this separation energy suddenly decreases very steeply when you cross a magic neutron number. So here at 20 and here at 28. So the slope of the curve suddenly changes drastically. And so at n equals 32, this was seen at ISOLDE in 2013. And then at n equals 34, it's not a very strong decrease, but it was suggested that this could be also a hint for a new magic number. So the question is then, are these indeed new magic numbers? And these are things that are now further explored also through other techniques. There are many different mass measurement techniques. The penning trap, as I said, was used in the past very routinely and is still being used. It's a very high precision technique, but in the last years, there are 2 techniques that have been developed that are more sensitive, for example, or because they are faster, like the multi-reflection time of light gives access to very short-lived isotopes because the whole manipulation can be done in less than 20 milliseconds. And still they are able to separate many different isobars from each other. Of course, the precision on the mass is a bit less than in the penning traps, but it's still quite good. The phase imaging ion cyclotron resonance technique, which is based on the penning trap principle, but which uses a specific way to visualize the ions, is a very performant technique because it's extremely sensitive. So it allows to perform measurements on very weak beams of just a few ions. And it allows to distinguish excited states within one particular isotope. So here, for example, 129 cadmium, the ground state has, of course, 0 energy, that's the reference. And this angle here is a measure for the excited state energy of the first isomeric state, which is known to be a 3/2 plus. So this gives very interesting nuclear structure information and is also in combination with laser measurements a very powerful technique. So let me now move to the measurements of nuclear moments, spins, and radii, which are probes, direct observables of the nuclei. The spin and the magnetic moment give us information on the quantum orbit that is occupied by the valence nucleons. And so it gives information on how the nuclear wave function is composed or about the single particle behavior of the last nucleons, whereas the quadrupole moment and the mean square charge radius are giving us information on the shape or on the size of the nucleus. And these observables can be calculated then with state-of-the-art nuclear models, and through comparing our data with these models, we provide a very strong test of the models, and we also can provide input to further improve the data, the models. So in laser spectroscopy, what we measure is we look at the hyperfine structure in a free atom or an ion. So electrons are known to have fine structure levels with a certain electron spin J. And so by then shining a laser between such two fine structure levels with a specific wavelength, we can make resonant excitations of from this level to that level. However, because the nucleus has also a spin, there will be an interaction between the nuclear spin and the electron spin, giving rise to the hyperfine structure. And here, for example, this is shown the level structure for copper-67, which has a nucleus spin 3/2. And if that interacts with these two levels, you get a splitting of these two levels. This is not at all to scale because this hyperfine splitting is typically of the order of microelectron volt, while here we are talking about electron volts. So if we want to resolve in our experiments these energy differences, we need to have very high resolution lasers. So have to excite these transitions one by one with each an individual laser frequency. And what you get then is typically this kind of spectra. So you can probe these excitation levels one by one. And then the position of these spectra, as well as the relative intensities, will give us information about the nucleus. So the distance between the levels here and also there are giving us information on the nuclear magnetic moment and the nuclear spin. And so, in fact, directly on the nuclear G factor, which gives information on the wave function, or on the nuclear quadrupole moment, which gives us information on the nuclear shape. And as I said, also the relative distances, as well as the peak intensities, are spin dependent. And so if we can resolve all the peaks, like in this particular spectrum here, we can also directly measure the nuclear spin. So this is in fact one of the only techniques where you can directly measure a nuclear spin. There's another observable that we get, and that is if we measure the spectra for different isotopes, like for manganese 55 up to 63, you see that the center of gravity of this spectrum is shifting as the number of neutrons is increasing. And this is a reflection of the change in the shape or the size of the nucleus. So it's a measure of the mean square charge radius. So in one experiment, we can really have 4 different observables from the data, and that's in fact because we have an overdetermined system here, because we have many peaks. So in this here we have, for example, I think 8 or 9 or 10 peaks, and we have 4 different observables which are all correlated with one another through one formula, so you can really get all the data independently. So let me show now an example of such an experiment, and that is from the resonance ionization laser ion source, which we can also use to do spectroscopy. So in this experiment, a molten lead target is irradiated with protons, and mercury isotopes are produced in the ion source, and they are ionized by sending 3 laser beams with specific frequencies into the ion source, where they are then ionized and extracted and then mass separated. And then the isotopes with different mass can be selected, and sent into different experimental stations to detect the signal of the resonance ionization. And the three signals, so yeah, here these are the three laser colors that were used. And then the first laser in this particular experiment is tuned to a narrowband mode so that you can excite each of the hyperfine structure levels one by one and individually resolve them. Now, to see the signal here, 3 detection stations were used. For the isotopes of mercury that decay through alpha decay, these isotopes were sent to the windmill, which is in fact nothing else than a carbon foil that is mounted on a wheel, and so many different foils are mounted. And then there's silicon detectors on the front and the back, which detect the alpha particle that is emitted. And then this can rotate to remove the activity to look for the next decay. It can also be sent to a multi-reflection time of flight mass spectrometer. This is for mercury beams that are heavily contaminated with isobars, and then you can easily resolve them here. And you can also send it to a Faraday cup in the case you have a very high intense current, for example, the quasi-stable mercury isotopes. So here you see the yield of the mercury ions that were produced, ions per microcoulomb, which is close to ions per second, as a function of the mass number. And so you see that near stability, you have several picoamps of beam, and experiments could be done down to 177 mercury produced at less than 1 per second. This is some sample spectra. What is interesting to note here is that the most exotic isotope that was studied had a peak intensity of 0.03 ions per second detected on resonance. Note here that although all the lines are nicely resolved, the resolution in the ion source is rather bad. It's of the order of 4.5 gigahertz, and that is because of the high temperature in the ion source. So this is due to what is called Doppler broadening. So the result from this experiment is shown here. So here you see the change in the mean squared charge radii as a function of the mass number of the mercury isotopes that were studied. First, let's have a look here at this spectrum. So what you see is that the shape of the isotopes is staggering enormously. Now, this was known before, but the measurements that were done before, already more than 30 years ago, I think, they stopped here at this isotope. So, in fact, we didn't know what would happen if we would remove further more neutrons from the mercury, and this is what was now achieved. So the earlier data were reproduced, but now we could add these data points here, showing that the shape becomes again more stable. So this has now also been able to be explained microscopically from the first time by comparing the results through large-scale shell model calculations of the Tokyo group. So the blue lines are calculations with the theoretical error bars, and you see that the reproduction of the data is extremely well. And then by looking more into the details of the calculated wave functions, it was seen that this staggering, in fact, is induced by a strong interaction between the protons and the neutrons in 2 particular single particle orbitals. And the population of these orbitals is enhanced in the isotopes where the staggering occurs. So this is now understood for the first time also microscopically. Another resonance ionization spectroscopy technique that has been developed in the last 10 years at ISOLDE is the collinear resonance ionization spectroscopy technique. This technique is developed to overcome the problem of the RILIS experiment, namely the very large line width in the experiment, so the low resolution. The point is that if we accelerate a beam which has a certain velocity spread due to the thermal heating into the ion source, so if we now accelerate this beam from an energy, let's say, that is room temperature up to a higher energy, then the energy spread remains the same, but the velocity spread is reducing, and that's just simply because of the relation between energy and velocity. And so this means that by accelerating our beam, the relative velocity spread is decreasing, so the Doppler broadening is strongly reduced by orders of magnitude. Additionally, it can help, like it was shown at Jyväskylä, that you can further reduce the energy uncertainty by adding a Cooler buncher, although at ISOLDE, the energy uncertainty is already quite under control, so it doesn't help very much to use the Cooler buncher. But the bottom line is that now you can perform experiments with a resolution of 20 to 60 megahertz. And that means that now you can resolve all the hyperfine peaks also for the lighter elements, which is not the case with the in-source technique. Okay, so as an example for nuclear structure, I didn't include one here, but I want to show how we use this experimental setup to study molecules for the first time. So radioactive molecules are predicted to be the most sensitive probes to look for physics beyond the standard model, for example, by measuring an electric dipole moment. So here you see the values of the electric dipole moment that have been, let's say, ruled out. So in the past, such measurements for an electric dipole moment were mostly done in atoms, and they were sensitive to the order of 10 to the minus 27 e-centimeter squared. And then experiments started on molecules about 10 years ago, and now these are gradually pushing the limits further down to smaller and smaller electric dipole moments, and the last one was published 2 years ago for thorium oxide. Now, what is special is that dipole moment studies in molecules have been predicted by quantum chemists to be more sensitive if the isotope in the molecule has a higher Z. Now, the highest Z, of course, is not thorium, the thorium element. Well, that's also one of the good ones. But radium, for example, has a very high Z, 68. And additionally, we know that radium, some of the radium isotopes are pear-shaped, which is another enhancement factor to be sensitive to a dipole moment. So by doing studies on such type of molecules, you could push easily this sensitivity to a dipole moment with another factor of 100 downwards, which means that you are really very competitive to searches for new physics beyond the standard model, for example, in the LHC, which is now in the order of 14 TeV, while here we would be sensitive to similar effects in the 100 TeV range. So this was a quite challenging experiment that was performed just before the long shutdown, and it was challenging because we had a lot of unknowns before the experiment. The first one was, could we produce radium fluoride molecules, and how to do that? So here the target team was very crucial to help us with that, and they found that if they inject the target with CF4 gas, then indeed radium fluoride molecules are being produced in the ion source and ionized through surface ionization. Then these ions are deflected through the mass separator and sent into our Cooler buncher, so the ion trap, because for the experiment we need bunched ion beams, not a continuous beam like it comes from the ion source. So the next question was, would the ions survive the passage through the ion trap? Then they have to go through the CRIS experiment, and in this experiment we don't do experiments on the ground state, so on the atom or the molecular ground state. So we don't do it on the molecular ionic state, but on the neutral molecule. And for this, it goes through a charge exchange cell, which contains the sodium vapor. So again, the question was, would the molecule survive, and would it end up in its grounds, in its molecular ground state? And then finally, we were shining with lasers onto these molecules with the aim to re-ionize them and then to deflect them onto an ion detector. so that we have a very clean signal, and everything that is not interacting with the lasers just goes straight. So here the question was what laser frequencies to use, because only theory was available on that, and the ranges that were predicted both for the first excited states as well as for the ionization potential were quite uncertain. So we had to have different laser systems in place, and in fact six different systems were installed to scan at the same time. So as soon as one resonance was hit, it was then checked with which of the laser systems it happened. And so like that, the first signal could be detected after just a few hours of measurement time. And it turned out that the signal here was very, very close to the predicted value. So the theory of molecular chemistry is really very good. So once this was observed, the signal, it was measured in more detail, and then also other excited states in the molecule were studied. And so, first of all, the vibrational excitations could be labeled, and also the lifetime of this excited state here could be measured to be less than 50 nanoseconds. Then a very important result that came from this work is that we have shown that radium fluoride ions can be laser cooled. The condition for that is that the decay from the first excited state back to the ground state has to be the dominant one. So in fact, this decay here has to be very strong, and the decay out of that state into another state should be very weak. And these transitions were measured for each of them and found to be very, very small. So this is okay. Then a second thing for laser cooling is the short lifetime of the excited state, and this was also proven. And the other one was that other electronic levels should appear well above that level here, and this was also proven because 3 more states could be identified, and they were found all highly above this first level that we were measuring. So this is a very important result, because now we have shown that we can laser cool radium fluoride, and so these isotopes can, or molecules can be used for very high precision studies after laser cooling. So with this, I would conclude my talk. So ISOLDE is now providing slow and accelerated radioactive ion beams up to energies of about 10 MeV per nucleon. We are using them for a dozen of different permanent experimental setups, and there's also room for a few traveling setups for research in nuclear physics, nuclear astrophysics, solid-state physics, biophysics, fundamental interactions and symmetries. And we are also now thinking about the future of ISOLDE on how to further expand it to serve the ever-growing users community. And with this, I would like to thank you for your attention.
Many thanks, Gerda, for the nice overview. I will try now to channel the questions on the YouTube to you, or just ask for the questions if there are some there on the chat. So you have discussed about the MINIBALL detector for reactive beams. There is a question from Professor José Ramón Peláez on that, and he's asking about the MINIBALL detector, which does not seem to have a 4-pi coverage, whether this is made on purpose or is limited by construction.
It has not a full 4-pi coverage, but it's quite close. Let me go to it. Yeah, here. Okay, so yeah, you see, yeah, I think in the figure it's not showing all the detectors. Let me check. So we have, is it said here? What's the coverage? No, it doesn't say exactly how much we are covering of the 4-pi. So if it's on purpose, I think that was the choice of the collaboration. It's probably also a matter of money. But as you can see, I think it could be close to 4-pi, because here this is another figure Of course, to make the picture, sometimes some of the detectors are removed just to be also able to see the inner detector.
Can you show maybe the picture? We cannot see it, I think.
Ah, you don't see it. Okay.
No, I don't know if you could. If not, is.
Let me check. Did I stop sharing this?
No, the beam. The slides are being shared, but they are. I can only see the conclusions.
Okay. So I have to go to another. Sorry, I have to go to the slide view. Do you see it now? Louis?
No, I can see conclusions. But,
so I have to. I will stop share and I will.
Well,
I will share it again.
As you wish.
Stop presenting. I don't know why this is happening. Okay, so now you should see it.
Yeah.
Okay, so yeah, this is here the picture with the detectors. And so, as I said, indeed, there's a hole. There's no detector here, for example, but I think it's removed to take the picture to better see the rest of the setup.
Yeah, so it's
exactly
basically as much coverage as possible, I think.
Yes, yeah.
My point of view.
Do you know the number of the coverage yourself, Louis?
I don't have the number with me, but it was
it's
made.
Quite close to 4 pi. Yeah. So, for example, this is another configuration.
Yeah, this configuration is with 8 clusters, and yeah, then you have the beam pipe and the spherical chamber for reactions. So I think it was pretty close. There were also, as you said, some limitations on the cost, but I don't have the number with me. Then maybe I may ask you about something about related to the implications of the mass measurements that you nicely described on related physics of interest for our institute. For instance, on double beta decay or related to that neutrino physics, whether you could comment on that, on some measurements that could be performed at ISOLDE, or where something has been done on that direction on the proposal.
Yeah, so there are, and I didn't cover it here in my presentation, but there are mass measurements ongoing. Plans to do some measurements, but I forgot the isotopes. It's related to this, is it holmium? Is it possible?
Yes.
Yeah, I know that the ISOTRAP collaboration has plans to do some measurements related to the double beta decay. But I don't have the details about it, I'm sorry.
Okay, and then I have myself a particular question on how do you see the strengths of ISOLDE facility in the world context. Now we have now RBF in Riken in Japan at full, I would say at full speed. F3 in the US is coming alive. There are, of course, fermentation facilities, but from your expert point of view, it would be nice to hear. I mean, what are the strengths of ISOLDE, or how do you see that in the world scenario?
Yeah. So first of all, these two facilities are based on a very different production scheme for the exotic isotopes. So they start from projectile fragmentation. Riken, for example, so the radioactive ion beam facility in Japan, which has already been operational for a while, the upgraded facility, is what I would call a discovery facility. They really have access to the most exotic isotopes. However, precision experiments like the ones I just presented here to measure the masses or to measure charge radii or nuclear spins, so details of the nuclear structure, they require well-qualified beams, so with a good beam emittance, with a good beam purity, and these beams are much better provided at ISOLDE facilities. Also, in terms for nuclear reactions, so the beams that are coming from projectile fragmentation facilities are in-flight exotic beams, and they typically have quite high energies of the order of tens to 100, well, more close to 100 MeV per nucleon or even more. So for the nuclear reactions that I was presenting, Coulex excitation and transfer reactions, which are really ideally done at these energies of 5 to 10 MeV per nucleon. Again, the advantage at ISOLDE is that not only the energy is the right energy of the beam, but also the beam quality is very good. So it's pure beams with a well-defined beam spot, while at fragmentation facilities, for example, the beam spots are typically of the order of a dot of centimeters large, while as at ISOLDE it's millimeters. Now, for the American facility, which will come very soon operational, there, of course, they have the gas cell and the stopping, and then the reacceleration, and then, of course, they have very similar beam properties as ISOLDE for these isotopes that have been first stopped in a gas cell, extracted, ionized, and then reaccelerated to 40 keV or even 10 MeV per nucleon, whatever. So what's different with them is that it's probably the type of isotopes that we are going to study. Some elements and some isotopes are better produced at those kind of fragmentation facilities, while others will be still better produced at ISOLDE. For example, I would say the lead region and the trans lead region is a typical one that is much better produced at ISOLDE, for example. But there's other regions of the nuclear chart where we will still be competing. So I think the two facilities or the two types of facilities have their pros and cons. But to go to the really exotic cases, so if EVRIP becomes operational with their low energy facility, then we have really to see how that will go. So if they have indeed the highest intensity for all isotopes, then we have to see. But I'm not so pessimistic about that, in fact.
ISOLDE is running, whereas EVRIP still has to come alive. So
exactly, they still have to start.
To have a perspective on
and the chart of nuclei is very large, so I'm really sure that there's absolutely still a lot of things to be discussed or to study at ISOLDE. And also, not all the techniques that we have at ISOLDE are available, of course, at EVRIP at the moment, although they are, of course, building up fast. They have a panning trap, they have now a collinear laser line, they will have dedicated decay spectroscopy, they will have reaccelerated beams, but as I said, they are just starting. Huh?
Okay, thank you. I do not see more questions, but maybe if I may, because you mentioned specifically about these molecules, I think it's very impressive work. I know the technical difficulties also we try to highlight. Is this a program that will be expanded at ISOLDE? Is something that will be, because I think it's rather unique, yeah? So
it is unique, yes. But it's not so, well, how to say, it attracted a lot of attention in the world. And we do plan to continue that program. So we are currently leading that program, but there are plans already at EVRIP to build a dedicated setup for that, as well as at TRIUMPH. And we are collaborating with them to help them with that. The point is, radioactive molecules have never been studied before. Yeah. And it's a field we have just looked at the possibilities. Such molecules can give us information which was not accessible till now from stable molecules in different fields. This is fundamental physics research, so beyond standard model physics research, but also for nuclear structure. It could be that we have access to nuclear moments that we couldn't see in the atoms, but which will become accessible in the molecules because the fields are larger in the molecules. Also for waste, so nuclear power plants and accidents in nuclear power plants, one of the problems is molecular behavior. And of course, this is also with radioactive molecules because these are the molecules that are formed there. So knowing the details of the spectroscopy of radioactive molecules on all levels, we are now just at the starting point, but the high precision level, but also just the rotational and the vibrational spectra is really important for a lot of fields. And I think there's a huge interest to start this at several radioactive beam facilities.
Okay, so well, I don't see any more questions. I wanted to really thank you for the very nice overview on SOLID and some of the physics, and also I profit to thank you for agreeing to be part of the IPARCOS overseeing committee, which is appreciated from our side. I think it's interesting and important for us to have experts on board and help us. Mm-hmm. And with that, I thank everybody for attending and the organizers again. And I will stop here. Thank you very much, Gerda.
Okay.
Pleasure.
Thank you, Luis.